Welcome students for this lecture 15th on symmetrical components to analyze three-phase unbalanced circuits. We were discussing about three-phase unbalanced system, and in that context we have discussed the concept of symmetrical components. In general, the power remains constant, the energy remains constant when you transform the variables from one set of axis notation to another set of axes. So we have seen when we transformed ABC into alpha beta, the power was constant, and now when we transform ABC into positive, negative and zero sequence component, power will remain constant. We can prove it by this derivation. So as I said in the previous class, the apparent power, this is called SB complex. The bar notation is for a complex quantity, that it has a real and it has a imaginary component. So this SB, B is basically known as vector or geometric apparent power. Vector or geometric apparent power. Now this name has a special meaning to the definition of apparent power. So as the name indicates, vector means it is the phasor sum of each phase power. For example, we can write if the overall power is P, okay, and the overall reactive power is Q, then it is P plus JQ, where P represents PA plus PB plus PC. So this is PA plus PB plus PC. Okay, and Q represents QA plus QB plus QC. Or we can also think of individual phases with active and reactive powers together. For example, this is also sum of PA plus JQA plus PB plus JQB, and then the C phase PC plus JQC. Or we can also write in form of individual complex apparent power for each phase, that is SA plus SB plus SC. Which can also be written as the product of the voltage phasor and the current phasor conjugate, that is BI conjugate. We have proved this. The complex apparent power can be written as BI conjugate. So this can also be written as BA into IA conjugate plus BB into IB conjugate plus BC into IC conjugate. And this is known as the inner product of two column vectors. So here you have to add the conjugate term here, and this become the inner product of voltage row vector and current column vector, which can be written as BA BB BC transpose. Okay, this is transpose here, and then this into IA IB IC conjugate. So this is called as inner product of B and I column vector, or voltage and current phasors column vector. Now to prove that power, what we will do, we will simply expand this in terms of the sequence component. So we express A, B and C in terms of the A0, A plus and A minus. So you know that this ABC can be transformed to BA0, BA plus, BA minus, or we can write ABC in terms of the 0 plus and minus row matrix AABC. then transpose of this, and the remaining term is current column vector transpose, and this term is taken here. So first is ABC transpose, and then IA0, IA plus and IA minus. Now as you know that the transpose of matrix AB is nothing but B transpose A transpose. If I have matrices A and B and I find out AB transpose, this is nothing but B transpose A transpose. So this becomes first the voltage transpose, that becomes BA0, BA plus and BA minus transpose here, and then into AABC transpose. And then here it is AABC conjugate, and this is IA0, IA plus, IA minus conjugate. Now if you solve this part of the matrix multiplication, then you will see that this multiplication comes out to be 3 into identity matrix. You need to solve yourself to verify results with me what I have presented here. So multiply the components of this matrices, transpose and conjugate, you will see that the product is 3 into I. I is an identity matrix whose elements are 1, 0, 0, 0, 1, 0 and 0, 0, 1. So this will not affect the result. Basically it is basically 3. 3i basically means 3 into this vector. So this multiplication actually becomes this one. 3 into BA0, BA plus, BA minus transpose. Transpose will come here, and into IA0, IA plus, IA minus. If you multiply these two terms, you will get 3 times of BA0, IA0 conjugate plus BA plus, IA plus conjugate and plus BA minus, IA minus conjugate here. Now what is this term? BA0, IA0 conjugate is nothing but 0 sequence power in phase A. So this is actually 0 sequence power in phase A. What is BA plus, IA plus conjugate? This is positive sequence power in phase A. And BA minus into IA minus conjugate is negative sequence power in phase A. 3 times of this. So basically 3 times means that this 3SA0 plus 3SA plus and plus 3SA minus. So 3 takes care of the apparent power of the other phases. For example, if we expand this, then you will see that this is 3 here into SA0 complex, 3SA plus complex, 3SA minus complex. As if the 3SA0 takes care of SA0 plus SB0 plus SC0. So this is actually SA0, okay, SB0, SC0. So this 3 SA0 is taken care by this term, and 3SA plus is taking care of SA plus, SB plus and SC plus. That is positive sequence apparent power. And 3SA minus, this term is taking care of, what is that term? SA minus, SB minus, SC minus. Since they are identical, that's why the term 3 is there. We can also write actually in form of this equation. If you don't want to write 3, it becomes S0 plus S plus, I think I have given in the line below, and minus. This is given here as well. So this becomes S0, S plus, S minus. Now this S0 accounts for this one, and this S plus accounts for this one, 3 into SA plus or SA plus plus SB plus plus SA plus, and the S minus accounts for this one, which is same as 3 into SA minus. So this is the description of complex apparent power in zero sequence, positive sequence and negative sequence components, also its value in terms of the ABC. You can also use this notation, that is BA0, BA plus or B minus as 1 by root 3. This is called unity transformation, where the magnitude is basically 0, plus and minus. It is not BA0 or it is not BA plus, it is not BA minus, because this B0 represents all three phases A, B and C. That's why 1 by root 3 has come here. And if you use these expressions, then the nature of the apparent power will be this one. Simply it will be S0, S plus, S minus. Okay, this here S0 will be nothing but V0, I0 conjugate plus B plus, I plus conjugate plus B minus and I minus conjugate. Please note, we have not used here A and B and C subscript because 0 represents A, B, C, all three. Similarly, the plus represents all three, A plus, B plus, C plus here. And minus represents BA minus, BB minus and BC minus. So depending upon the requirement, we can use any of these transformation, 1 by 3 or 1 by root 3. But we must know the reason and the logic behind why we are using 1 by 3 or why we are using 1 by root 3 transformation. This will bring a significant clarity that why we are using a certain transformation. Okay. Now we have learnt that the complex apparent power can be resolved in terms of the zero sequence, positive sequence and negative sequence component. We can also find its value in terms of the real and reactive power using this transformation. For example, as I said that SB is nothing but 3 times of BA0, IA0 complex conjugate plus BA plus IA plus conjugate and BA minus IA minus conjugate. If you expand in terms of the real and reactive powers, then we can find out the cosine and sine terms. For example, if we resolve this into sine and cos, we will get BA0 IA0 cos phi 0. So this is the real part of this. The imaginary part of this will be J BA0 here, IA0 sin phi A0. This is the imaginary part of the BA0 IA0 conjugate. So this is the imaginary part, this is the real part. Similarly, for second component, this is the real part, that is BA plus IA plus cos phi A plus, and this is the imaginary part, BA plus into IA plus sin phi A plus. And similarly, we can resolve the third one, that is BA minus IA minus complex conjugate in terms of the real and imaginary components, and these are BA IA minus or BA minus IA minus cos phi A minus, and then BA minus IA minus into sin phi A minus. So we can express directly in terms of the real power and reactive power components using cosine and sine functions, which is similar to that just we have described. It is the 3 times of the PA0 and QA0, then PA plus, QA plus, and PA minus and QA minus, which is similar to what we have just found: PA plus JQA, PB plus JQB, and PC plus JQC. Alright, and which is again same as PA plus PB plus PC, P equals to PA plus PB plus PC, or 3 times of PA0 plus PA plus PA minus, which is also equal to P0 plus P plus P minus, because P0 is sum of PA0, PB0 and PC0. And similarly, there is a Q, the sum of A, B and C reactive powers, or 3 times of each phase 0 sequence, positive sequence, negative sequence reactive power, or sum of the directly Q0, Q plus and Q minus. Now let us come to more important thing, that is about the apparent power in terms of the sequence component. Now as you have seen that we have now resolved ABC axis apparent powers in terms of the 0 sequence, positive sequence and negative sequence apparent power. Then we can see into more details of these terms. For example, S0, that is the 0 sequence power. This is a scalar quantity. There is no bar over this. This is actually a mod of S0 bar. The absolute value of S0 bar is basically S0. This is called scalar 0 sequence power. This is called complex 0 sequence apparent power. And obviously this must be P0 square plus Q0 square, or it could be equal to simply 3B A0 I A0, this one, and you can take mod of this. Similarly, we can write for S plus in terms of the P and Q. So S plus will be SA plus, and this will be the sum of the square root of square value of P plus and Q plus, corrected, Q plus. This is again equal to 3 times of VA0, BA plus, this will be equal to 3 BA plus and IA plus conjugate and mod of this. Similarly, we can write for negative sequence, that is SB minus, that is S minus equal to SA minus, this is not SA actually, it is S plus, so this is A, you can drop it, okay. So correct it by saying that it is S plus, and this is S minus, and mod of this, which is same as P minus square plus Q minus square root of that, and this is also equal to 3 times of BA minus and IA minus conjugate and mod of this. Again we will write in terms of the ABC component. So this geometric or vector apparent power SB is therefore complex or phasor addition of P and Q, which is having the individual components of PA, PB and PC, and then in the reactive power we have plus JQA, QB, QC. So this is summation of QA, QB, QC, or we can sum them on individual phase basis, or SA, SB and SA. So you see there is a complete equivalence between the symmetrical components as well as ABC components. The very interesting part or very important part of this discussion is that why this is called vector power or geometric power and what is its significance. So as I said, that vector power is nothing but the mod of SB, which basically means the mod of SA, SB and SC. So first you add A and B and C, complex apparent power, and then you take mod of this. But then you may ask that why we should take mod of the overall apparent power. Can we take the mod of individual apparent powers and sum them? For example, there is another possibility. The possibility is that we can add the mods of each individual phase apparent power. Are you getting the point? We can add the mod of individual apparent powers for the phases. So this is SA bar mod. See the notation. SB bar mod, SC bar mod. If we add the apparent power like this, then this is called arithmetic power. Note the term arithmetic, because this is the arithmetic sum of apparent powers for each phase. This is not the vector addition, this is the arithmetic addition. So there are now two apparent powers. One is the vector apparent power and second is arithmetic apparent power. From these two expressions, actually, if you look this expression, okay, here, and you look this expression, you can tell that the arithmetic apparent power shall be equal or greater than the vector apparent power. Am I correct? This condition is always true. At most it is equal, but it will be greater than the vector apparent power. Why it is so? Because we are taking the mod of individual sequence power or individual phase powers. But here we are adding each phase complex power. This is a phasor sum. This is the arithmetic sum. Now this can be very well understood by this expression, this diagram. You can see here, these are the different power components for each phase. For example, this is PA, this point, from here to here, and this is QA, this makes SA. So SA is the apparent power of phase A. Similarly, for phase B, this is PB, this is QB, and this is SB. Then for phase C, this is PC, this is QC, okay, and this is SC. Now if I add them together, this plus this plus this, arithmetically, then it becomes the arithmetic apparent power. So I have added this here, okay. This is the SA up to this point, and from this to this, SB here. So this is SB from this point to this point. This is SB, okay, and from this to this it is SC, SB. From this to this is SC. If you look from this to this is SC, from here to here. And if I add them, we will get SA. This point is SA. So this whole thing is actually SA, from here to here. If I take from here to here, this is SA. Okay, and what is the SB? SB is the vector sum. So if I add the SA, SB, SC on vector basis, like it is a one vector here actually. This is one vector, this is second vector, this is third vector. So if I add them on the vector basis or phasor basis, we will get this term. Okay, and if I resolve back on the x-axis, this will be the SB. So if you see it from this length, it is the SB. So you see a difference between the SA and SB. This is the difference that you got from SA and SB. This difference is the basically difference of the two apparent powers. And you can see here that SA is greater or equal to SB. Now based on that, the two power factors can be defined. Number one is the arithmetic power factor, number two is the geometric or vector power factor. So based on this definition, you can say we can define the power factor. The first power factor is power factor vector based definition, that is Py SB, and another power factor is arithmetic based, P of A equals to Py SA. Obviously, since SA is greater than or equal to SB, so power factor A is less or equal to power factor vector. So we have now two apparent powers. Number one, vector apparent power. Number two, arithmetic apparent power. Based on this, we have two power factors. The one is arithmetic power factor. Number two, the vector power factor. And the arithmetic power factor is less than the vector power factor because SA is equal or greater than SB. Okay. Now we will take one example and try to see that what is the significance of these terms and how they are useful in the design of the feeder network or transmission network. So this is one example. This example is given in the NPTEL book that I have given you. This example tells about a three-phase unbalanced system. As you can see that the three-phase supply is supplying the resistive load between point A and B. So this point is A and this point is B. The other two phases are not carrying any load. The load is between point A and B. So for this system, we have to find what is the power supplied to the load and what are the feeder losses. Voltage B, A, B, B, BC are balanced. So voltage here A, B and C are balanced. So this is BA here, this is BB and this is BC. This is BA dash, remember. This is BB dash and this is BC dash, BN dash. These voltages are balanced. We have to find the various power components in this system. So let us find out, to find power we need two parameters, voltage and currents. Okay, because the power is product of voltage and currents. Now let us find out the losses or the output power. So output power will be nothing but the power consumed by this load. And what is that power? It will be voltage into current in this component R, or voltage square by this R. Okay, so I know this voltage. This is line to line voltage. This is BAB. Okay, so I can say BAB square by R. What is BAB? Since BAB is balanced, so root 3 B square YR. So this will be 3B square by R. Fine. So you can see that the power dissipated by this load will be 3B square by R. And this is nothing but the output power P0. So this much power is supplying to the load. Now to find out the individual phase powers and the current components of the each phase as well as the power factor of each phase, we need to find out first the currents. Now what is the current flowing in this circuit? The current IA is nothing but BA minus BB by R, because this is the current IA. So this voltage divided by resistance. So if you find out IA phasor, nothing but BA minus BB by R. If you solve this, then you can find this is nothing but root 3B. If A is the reference phasor, BB is negative sign, the angle will be 30 degree divided by R. And if you find the magnitude of this current, mod of this will be root 3 YR. This is RMS value of the A phase current. What about IB? If you apply the Kirchhoff current law at this point, okay, so IB plus IA equal to 0, which actually means that IB is minus IA here. So IB becomes nothing but minus root 3 B by R angle of 30 degree. As you can see from this expression. Now let us find out the losses in the feeder. The losses in the feeder will be I square into R for each phase. Since the current is flowing in this and this only, current is flowing here and here, this current is 0, this current is 0. So losses will be only in these two feeders, that is IA square into R plus IB square into R. So these losses will be root 3B square, root 3B by R square, this is IA, you can say, magnitude of IA. Similarly, this is the magnitude of IB, which are same. So the total losses in the feeder will be 2 times of R by R, 3B square by R. What is this? This is actually output power. So this is twice of R by R into P. P0 you can say output power. Now we can think of a 3-phase system supplying 3-phase balanced load. Imagine that there is a equivalent balanced 3-phase circuit which is supplying the same amount of power. How this is possible? We can take 3-phase system supplying power to a resistive load or to identical resistive load in all 3 phases. In that case, the power will be 3 into I square into R. This is A, this is B phase, this is C phase. Now we have 3-phase balance system. So we have this R and this R and this R. Okay, this is C phase and this is B phase. This is neutral here. So this is now BA, this is BB, this is BC, this is BN, and this is IA, this is IB, this is IC. Since they are balanced, so power will be same. And that power is nothing but 3B square by R. What will be the losses? The losses will be 3 into I square into R, because in neutral the current will not flow. Why current will not flow? Because IN will be sum of IA plus IB plus IC. Since currents are balanced, so their sum will be equal to 0. Therefore, there is no current in this, and therefore there will be no loss in the neutral. The only losses will be in phase A, B and C, and hence the total losses in the feeder will be 3 times of B by R square into R. That becomes R by R into 3B square by R. If you compare this case, 3-phase balance case, with the same output power, P0 is same, that is 3B square by R. But this is the case of balance, and the previous case was case of unbalance. The power is same. You can see here this power and this power is same. But there is a big difference. The feeder losses are here twice of R by R, 3B square by R, and here the feeder losses are only R by R, 3B square by R. It means that the losses are 50% less than that of the unbalanced 3-phase system for the same output power. So we learned from this very interesting point that the losses becomes more if the system is unbalanced. So we learned that the losses becomes more when system is unbalanced. Now the second case which I have discussed is like this, where we have 3-phase system perfectly balanced. Okay, and for that case we just have found out that IN equal to 0 because balanced 3-phase system, and P0 is same as the previous case, 3B square by R, and losses are basically R by R into P0. This is the balanced case. In case of unbalanced case, this is twice of this. This is very important point. Now let us find out the individual phase powers. That is SA, SB and SC, and find out their vector apparent power and the arithmetic apparent power. Now you have seen that IA is nothing but root 3 B by R angle of 30 degree. So let the current RMS be I, then angle of I is actually 30 degree, and this 30 degree angle has to be conjugated. So it becomes actually BI angle of minus 30 degree. And this gives the expression BI cos 30 minus J BI sin 30. This leads to the value root 3 BI by 2 minus J BI by 2. Then we can find out the real power, which is PA is root 3 BI by 2 and QA is minus BI by 2. Similarly, we can find out the complex apparent power for phase B, which is BB into IB conjugate. Now if you substitute the value of BB, which is B angle of minus 120 degree, and the current for B phase is I angle of minus 150 degree, and conjugate of that, this is angle, so I angle of minus 150 degree, and conjugate of this I. This becomes BI angle of 30 degree. So because of plus 30 degree, the sign is positive here, and therefore the active and reactive powers are root 3 BI by 2 and BI by 2. These are expressed here, root 3 by 2 BI, and QB is BI by 2. For C phase, the powers are 0 because in C phase there is no current, and therefore PC and QC and SC all are 0. Now if we find the total active power, The total active power is given by capital P, which is the sum of PA plus PB plus PC. And if you see the previous expressions, you can find that PA equal to PB. This is PA and this is PB, and both are same. And you see the QA equal to minus QB. So since they are same, the total power is 2 into root 3 Bi by 2, which equals root 3 Bi. And if we substitute back again the value of I, which is root 3 B by R, then it becomes 3B square by R. And the total reactive power is also sum of QA plus QB plus QC. Since QA equals to minus QB, the sum of the reactive power is 0. And that looks quite obvious, because if you see the network, it is purely resistive network. The supply is supplying the purely resistive load. Hence, there cannot be any net reactive power. Nevertheless, the individual phases experience the reactive power. You can see phase A has reactive power of minus Bi by 2, and phase B has reactive power of Bi by 2. So if we look in terms of the phase angle, then I can say here the power factor in phase A is therefore cos 30, which is 0.866 lead. This is lead. And for phase B, the power factor is cos 30 degree. Here it is minus 30 degree, because the current is lagging the voltage by 30 degree, and therefore this is 0.866 lag. So what do you see? That although the net reactive power is 0, but the reactive powers of phase A and phase B are not 0. In fact, they have some finite value and they are opposite of each other. If you look phase wise, then you can say the supply of phase A experiencing a capacitive load because the current is leading. Similarly, the supply of phase B experiences the inductive load because the current is lagging. However, there is no capacitance, there is no inductance in the circuit. Then why supply is experiencing the leading and lagging power factor in phase A and B respectively? The reason is the unbalance. Because of unbalance, the current has a phase shift of 30 degree lead for phase A and 30 degree lag for phase B, and that creates the reactive power and hence the power factor. Now let us come to the computation of the apparent power based on the vector and the arithmetic. The vector apparent power is given by SB, which is P square plus Q square root of that, or which we can simply say that it is the mod of the total complex apparent power. Now since Q is 0 and P is nothing but 3B square by R, so SB is same as P. From this, the ratio P by SB will come as 1.0. This implies that the power factor based on the vector apparent power is 1.0, and this is written here. Now if we find out the arithmetic apparent power SA, so SA is nothing but the mod of individual complex apparent powers in phase A, B and C. Now SC is 0 obviously, so this goes to 0 value, and SA and SB are same value. Basically the mod of SA is nothing but BI, and mod of SB is also BI. Okay, so this becomes 2 into BI. Now we replace the value of I, which is root 3 B by R. So this becomes 2 into B into root 3 B by R. Then we simplify in terms of the output power. So this becomes 2 B square. We multiply by root 3 and divide by root 3. Then this becomes 2 by root 3, 3b square by r. This 3b square by r is the real power p. So this becomes 2y root 3 into p. This is SA, and therefore p by SA is nothing but opposite of 2 by root 3, that is root 3 by 2. And this root 3 by 2 is 0.866. So what do we see here? That the arithmetic power factor is same as the power factors of the phase A and phase B. So when we design the power network or distribution network or transmission network or feeder, we have to take the worst case, or you can say we have to take the least power factor. For example, here I will choose the arithmetic power factor for the design of the feeder because it gives me more margin of safety for the current, or it will take care of the overrated current because of the unbalance in the system. But if three-phase system is balanced, then these two power factors and two apparent powers are same. This is another interesting observation, that in case we have three-phase balanced system, for that case the arithmetic power and the vector power are same, and hence the power factor based on these two definitions are also same, that is 1.0, which is quite obvious. Basically it means to say that I have a resistive load of value R in each phase, then power factor will be unity, and the vector apparent power and the arithmetic apparent power will be same. But if this is not true, then this relationship holds true between the arithmetic and the vector apparent power, that is PFA is less or equal to PFB, because SA is greater or equal to SB, and therefore the PFA should be less or equal to PFB, and for the design of the network parameter we will choose the value of arithmetic power factor. In the next class we will discuss one more apparent power, that is called effective apparent power, and we will find out the power factor based on the effective apparent power. We will see that the power factor based on the effective apparent power is much more practical than the arithmetic apparent power.